Well, good evening. I want to welcome our guests, our students as well. Welcome to this senior design project presentation for this academic year. In a moment, I'm going to turn over to our students. There are two projects that will be reviewed in this particular session. This is Channel C. The first project that you will hear about is entitled the Scroll Expander. I'm Dr. Gia Richards. I'm actually the advisor for this project. The students involved in this project are Miranda Griffith, David Harju, Bethany Henn, Jessica Kimbrell, Sean Klein, Garrett Rook, Samuel Sherman, Andrew Thompson, and Jared Zimmerman. So at this point, I'm going to turn it over to Miranda Griffith to begin the presentation.
Thanks, Dr. Richards. So to introduce you a little bit to this topic, I will first discuss the reason and the problem we're attempting to solve, which is an increased need of electrical energy storage. So the United States Department of Energy is predicting a 2.1% increase every year until 2040 in power demand in the United States, raising final energy consumption from 19% in 2018 to 24% in 2040. This is mostly due to an increase in electric travel and vehicles. And additionally, a shift to renewable energy sources will cause an increased need for energy storage, as renewable energy often relies on sources such as the sun and wind, which are not always readily available during peak demand hours. So electrochemical batteries are a potential solution to this problem. However, current lithium-ion batteries come with some challenges, including small capacity to store compared to the needed storage of this technology, as well as a short life cycle, only around 300 to 500 cycles of a battery. So because of this shortage in energy storage, Carnot batteries are being explored as a potential solution. So in the bottom right of this slide, we have an example of a Carnot battery. In this type of battery, energy is stored in the form of heat rather than by a chemical agent. During the charging process, electricity is converted into heat and held in a high temperature container. This is seen in the left-hand part of the picture. And during the discharging process, a temperature difference between the hot and cold containers allows for the stored heat to be converted back to electricity. There are a couple main commercial contenders that are building Carnot batteries. These include companies such as Ecogen, Highview, and Malta, which Malta has received around $50 million in investments to their thermal energy technology. Also, just for a frame of reference, large-scale Carnot batteries such as these typically have a round-trip efficiency in the 60 to 70% range, but the smaller system application, which we will be discussing today, is more around 50% or so. So none of these contenders commercially, however, are attempting to build Carnot batteries at the residential or building scale. And because Carnot batteries rely on the transformation of heat into a hot temperature source, and since hot water is already contained and supplied in residential homes and buildings, it's a unique opportunity to use already available sources of energy. So, for example, a hotel typically uses its hot water in the morning hours when guests wake up and get ready for the day. In the remainder of the day, the hot water container is normally just unutilized. So this is a great example of how thermal energy storage can utilize already existing building systems to store energy in a more efficient manner. So there were two things that our group had to do in order to better understand this technology. The first was to test a reversible heat pump engine using an organic Rankine cycle. And the second was to understand the size and scale needed to store the appropriate amount of energy in a residential or building application. Just so you guys know, other research and development projects attempting this small-scale Carnot battery technology include Marconi University in Italy, who in 2017 successfully converted a scroll compressor to an expander. Their system is shown on the bottom left of the slide. Also Chester in Germany as of 2020, as well as a New Zealand group shown on the bottom right, their system shown on the bottom right, are in the process of developing this technology as well. However, to our knowledge, no wide-scale research in creating Carnot batteries for small-scale energy storage is being conducted in the United States. So with that, I'm going to pass it off to my teammate Sean Klein, who will discuss the testing of the air system and how this informed our model and component selections.
So as Miranda mentioned, one of our goals was to create and test a reversible heat pump, which we achieved by taking a scroll compressor from the air conditioning in a car and running it backwards. But Jared will talk about that a little bit later. The first step in constructing our reversible heat pump was to run tests on the expander itself, which we achieved by running air through the expander. And this is the air test that Miranda was talking about a moment ago. With that in mind, the 2019 to 20 capstone design team ran some initial air tests on the scroll expander by just running air through it to get some data concerning the relationship between the angular velocity and the volumetric flow rate. Unfortunately, though, the design team was sent home with everybody else when we all got quarantined, and they were unable to get any further in the project. And that's where we picked up in the fall. So we decided to complete the air tests and repeat them in order to confirm the data and just familiarize ourselves with the expander. And you can actually see on the right in this picture, there's me, Jared, and Dr. Richards running the scroll expander. And if you look at the light bulbs in the bottom, that's the load on the light bulbs. So we showed that we can actually produce power with the expander. And once we had this initial data, which is what you see in the graph on the left, we were able to begin selecting components and designing the full organic Rankine cycle, which I'm going to let Garrett Rook talk about.
For my portion of the presentation this evening, I'll be discussing the development of the model and the methods used in the assembly process. The goal of our model and project was to create an engine using a refrigeration compressor. When the design of the system began, an isentropic assumption was made. In layman's terms, all the thermal energy that was put into the system was expected to be returned as work output. This can be seen in the figure to the right, noticing that the line between point 3 and point 4 is vertical. In practice, there will be losses within the system, but seeing as this type of system is new and very little is known about it, this assumption was necessary and gave us an idea of what to expect. The design points were based on the available water temperatures. The upper limit was set at 122 degrees Fahrenheit. The lower limit was set at 59 degrees Fahrenheit. It was important to match the pressures to the temperatures to ensure smooth operating conditions. The peak pressure was set at 174 psi, and the lowest pressure was set at 73 psi. The qualities were important as well. Quality is defined as the amount of vapor per total amount of fluid. This is because a pump cannot circulate vapor, and if the liquid gets into the scroll, problems could occur. After the model was complete, several relevant results were found. One being the maximum power output was 0.49 kilowatts. This does seem a bit low, but for a low temperature application, it was to be expected. Now we'll move on to the flow diagram. As can be seen on the right, the flow diagram provides an illustration of the cycle and how it interacts with the system's primary components. The system begins with the pump. The pump's function is to take liquid and cycle it through the system. The next component is the evaporating heat exchanger. The purpose of the evaporating heat exchanger is to convert the liquid to a vapor. This is necessary to create the desired maximum pressure for the system to function. Third major component in the system is the scroll expander. The scroll expander is where the power is generated by allowing vapor to expand, thus creating power through a shaft. The final component in the system is the condensing heat exchanger. The condensing heat exchanger converts a vapor back to a liquid so the pump can effectively send the fluid back to the system. Unfortunately for us, the 122 degree Fahrenheit water supply fell through, so we were forced to use 113 degree Fahrenheit source offered by Grove City College, which hampered operating conditions. If you direct your attention to the image on the right of your screen, you can see the physical components of the system. Along with the primary components, several secondary components were added. A refrigerant recovery tank, the red circle in the bottom right, was added to collect any refrigerant released by our pressure relief valve, which is the blue circle in the bottom center. The pressure relief valve was set 200 psi to ensure all components were not going to fail due to pressure. The white foam insulation was added after the first test around the evaporating and condensing heat exchangers to help with losses due to heat. Located in the top center green circle of the image is the motor controller. The motor controller was used to manage the motor speed to allow a greater control over operating conditions. Then if you look at the green hoses jetting out from the system, those were water intake and exit hoses. They were used to bring water to the heat exchangers where heat was exchanged between the refrigerant 134A, our working fluid, and the water from Hoyt Hall. Some challenges we faced were specing parts that ensure safe operating conditions of the budget we had. All the components, we had to meet the maximum safety pressure of 200 psi, which, as previously mentioned, was what the safety relief valve was set at. This challenge was a team effort. As can be seen by the image, we were able to pull it off. In the end, the system came together well, and the team worked well together to meet the cut times and design challenges. David Hardy will speak next about the budget and build materials for the project.
So we started with a total budget of about $4,434, which was kindly granted to us by ASHRAE. And this turned out to be just about exactly what we needed. $2,400 was spent on the main components of the system, including the scroll compressor, pump, heat exchangers, motor, flow meter, pressure gauges, and thermocouples. The single most expensive item was the scroll compressor at about $425, although both the heat exchangers together cost $620. The rest was spent on the piping and fittings required to put everything together on the cart, as well as some safety measures to cover moving parts and potential bursts. Over $1,000 were spent on the pipes, hoses, and fittings alone, which was more than we expected it would cost at the beginning. In the end, we finished building the system with only $249.50 left, which we plan to spend on getting better thermocouples, as the ones we purchased were not as accurate or reliable as we would have liked. We also analyzed the system to check for any significant points of pressure loss. The two biggest concerns were the vapor lines and the heat exchangers. Our calculations showed that the main drops in pressure were in the suction and discharge lines going into and out of the scroll compressor, though the pressure loss was much higher for the outlet line. Using very conservative estimations, rough calculations based on the maximum operation of the system determined that there could be about a 14 psi pressure drop here. However, this could easily be dealt with by our pump, and we were also planning on running it, at least initially, at much lower speeds, at which the losses dropped to almost nothing. For the bottom liquid lines, the pressure drop at even the highest speeds were negligible. For the heat exchangers, we were not entirely sure what effects would be seen, as the refrigerant would be going from half-inch pipe to 2-inch inlets and outlets in large heat exchangers. The refrigerant inside was meant to be saturated, with both liquid at the bottom and vapor at the top, so we didn't think that it would create a huge problem. Overall, it was judged that, though these things would hurt the efficiency of the system, it would not prevent the system from running and doing what it was supposed to do. Now Andrew Thompson will talk about data collection and overspeed protection.
Hello, everyone. I'm going to be talking about the methods we used for data acquisition on the ORC system. In order to have an understanding of what was going on in the system during testing, we needed to be able to observe and record meaningful properties of the working fluid at various points throughout the thermodynamic cycle. We chose to collect pressure and temperature data at 3 points: the inlet to the expander, the outlet of the expander, and the outlet of the condenser. These locations were chosen specifically so that we could monitor the state of the refrigerant at key points in the cycle and determine whether or not the system was behaving as predicted. The pressure and temperature data would also allow us to calculate various system performance metrics such as efficiency. Additionally, we had a volume flow meter to track the flow rate of the liquid phase refrigerant leaving the pump, as well as a tachometer to monitor the rotational speed of the scroll. For the sake of easy implementation, all of the systems selected for use in the system were standalone units with their own individual displays.
Oh my goodness, this camera's on.
Why are the cameras on?
And his mic's on.
Given that the initial tests on the ORC system would be conducted with no load on the expander, We had concerns about the scroll spinning up to unsafe levels and presenting a hazard to the operator. To address this issue, we designed the assembly shown here. The expander, which can be seen on the left of the picture, is coupled to a centrifugal clutch on the right. The idea behind this design was to limit the maximum RPM of the scroll by dissipating excess energy through friction in the clutch. This was accomplished by fixing the output of the clutch to an immovable sprocket shown in the upper right-hand corner. To test the efficacy of this design, we conducted a test by driving the scroll with pressurized air. Jared will talk more on this point later, but the clutch engaged as intended and limited the speed of the shaft to around 2,000 RPM, which is well within the safe operating speed for the expander. And with that, I'll introduce Samuel Sherman, who's going to talk a little bit more about safety.
Good afternoon. I will be taking you through the safety aspects of our project by the use of the HAZOP analysis. Hazard and Operable Analysis, or HAZOP for short, is a structured and systematic technique for system examination and risk management. In particular, HAZOP is used to identify potential hazards and problems in a system, which in our case is the scroll expander system. So in other words, this is our own version of making sure that our tires are in check before we drive every morning. Using HAZOP, you cannot be afraid to ask questions about potential hazards or risk. These are standard procedures in the industry. As you can see on the screen, for pressure and temperature, we asked ourselves, what if the pressure or temperature goes beyond the values they are designed for? What are the consequences of this, and what is likely to fail? For the pump and electric motor, we asked ourselves, what happens if the pump leaks? What would we do to mitigate this? Are the wires properly grounded? And if not, what could potentially happen? For the flow meter, questions we considered were, what happened if the readings were inaccurate? Or what if the measurements stopped working altogether? What if the meter broke and blocked up the flow? What else could happen? For number 4, for the refrigerant 134A, we asked, what if the refrigerant leaked through the pipings? And is the liquid or vapor that's leaking, is it toxic? Based on our system, we identified 6 different potential hazards and mitigations taken to avoid them. For the first one, pressure, we installed pressure release valves, and in the case of an excess buildup, then the pressure release valves were opened and the refrigerant was released into a discharge tank. For overspeed, we had procedural controls installed in the pump, including the clutch, to avoid overspeed. As an additional precaution, we also made sure that we had an operator who was prepared to open the bypass valve to avoid this. For the electrical, we used GFCI on all equipment to safeguard against potential electrocutions. For mechanical, guards were built around all visible and non-visible moving parts, as you can see in the picture on the right. Now I'll introduce Jared, who will delve into the compressor and the expander.
Expanders can be quite expensive, but one way to get an expander on a budget is to take an automobile scroll compressor and convert it into an expander. This shows a basic scroll compressor cycle. In a scroll compressor, there's a fixed scroll, the white spiral in the picture, and an orbiting scroll, which is the black spiral in the picture. Low pressure vapor enters the inlet port and is compressed by the orbiting scroll until it reaches the exit port in the center. This process uses power to rotate the orbiting scroll. A scroll expander would be the reverse of this compression cycle. High pressure vapor enters the port in the center and expands, causing the orbiting scroll to rotate, thus producing power. Essentially, the only change is reversing the inlet and exit ports.
Can you hear me now?
Yeah.
Okay. All right, so we decided to attempt this conversion and purchased a sand and scroll compressor. The only modification we had to make was removing the reed valve at the exit port. The reed valve prevents vapor from entering the exit port, which is what we now wanted. The conversion proved to be a success after conducting a test with air. The video clip on the right shows us testing the scroll expander and clutch mechanism. using a strobe tachometer. We were able to measure speeds of up to 2,000 RPM, which did indeed engage the clutch. One of the final steps of the build process was filling the system with refrigerant. A refrigerant technician was needed to do this, so we had Lonnie Best from Huzzy's Refrigeration do this for us. He double-checked that our system was suitable for refrigerant, vacuumed the system of air, and filled it with R134A. With the refrigerant loaded, it would soon be time for testing. Since the system was designed to be mobile, it was decided that it would be tested outside due to safety precautions. The heat exchange fluid to be used would be the hot and cold water sources from Hoyt Hall Engineering Building. We tested the system on 2 different days, and unfortunately, both tests proved unsuccessful in achieving a pressure difference across the expander, thus resulting in no rotation of the shaft. The first day of testing was cut short due to our speed controller breaking. For the second test, a drill was used to power a pump due to a lack of speed controller, and ice was used to further cool the cold water going into the condenser. This was effective in significantly lowering the overall pressure, but we were unable to increase the pressure on the hot side to create a pressure difference. Upon further investigation, it turned out there was no real flow in the system. This meant either there was not enough liquid phase refrigerant going into the pump, or there was a problem with the pump itself. A third test was planned where we would put ice directly onto the pipes in hopes of getting the refrigerant to condense. We would also investigate the unloader pressure valve on the pump. Unfortunately, on the day we planned to conduct the test, we found out there was a leak in the system, forcing us to halt our testing efforts. In spite of these setbacks, we are confident that there is enough documentation to prove that what we are trying to accomplish is possible, and we would have been able to get the system running properly with more time. Moving into the next part of the presentation, we are excited for some of the possible applications for the system, which Bethany Hain will begin to discuss next.
As Jared mentioned, we wanted to look at the applications for our project in order to ground it in the real world and to see if a possibility to address energy issues mentioned at the beginning of our presentation. First, we wanted to see how feasible our system is so that we could actually convince someone to install it in their house. To do this, we estimated the size of water tank we would need to keep hot and cold water to store thermal energy and then pull it back out with our system. We started with a 2-tank system seen on the left, and then settled on the single hot water tank approach seen on the right, with heat exchange occurring with the ambient temperature of the air rather than with a cold reservoir, in order to maximize efficiency and minimize the tank size needed. We took our model and applied it to a real home's data. This home is in Pittsburgh, PA, and has solar panels installed on its roof. As can be seen in the graph, there are times when the solar panel generation exceeds the power usage of the home. During these times, energy could be stored using our system and then pulled back out to cover the nighttime hours when the sun isn't shining and more power is being used than is produced. The tank size for this case ended up being 475 gallons, which, to give perspective, is about twice the size of your hot water tank at home and could be buried underground for convenience. So this is feasible. We wanted to extend this to see if it would work for a college campus, so we did a similar analysis on several campus buildings, assuming rooftop solar power, much like our residential case, and we found that the small-scale local hot water tank storage system was not a feasible option for such a large application. However, if we look at some larger scale versions of our system, it could work for a college campus or similar sized facilities, as Jessica will talk about later on. So instead, we decided to dig deeper into residential cases, and we looked at real homes in the southeast, southwest, and northwest, in addition to the northeast case I mentioned in the last slide. The U.S. is vast and varied, so we wanted to make sure our system could work for many different climates. Estimated tank size changed depending on the nighttime demand of each home, but it remained a possible solution in each case. For the sake of comparison, Tesla's residential solar battery pack on average costs $13,500. We estimate the implementation of our system to be around the same for a small-scale residential application, but our system has the added benefit of hot water storage for hot water needs in the home. The tank would be about twice the size of the battery pack, but would also have a greater energy capacity. Overall, this shows that there are some exciting possibilities to explore with our system for residential energy storage purposes. Next, Jessica Kimbrell will talk about some more applications for our system.
The large-scale application we explored was a housing community in Canada called Drake's Landing. The thermal energy storage system allows the community to meet 90% of its residential space heating needs through solar energy. I thought it would be interesting to see if it was possible to apply the exact model used by Drake Landing to our campus. I selected the IM field next to the gravel parking lot, as can be seen in the image on the right. This IM field is ideal for the implementation of both the underground storage and the solar panels because it is a large open field, has limited shading from nearby trees, and is towards the edge of campus. The IM field area was determined by using the measure tool in Google Map, while the Drake's Landing parameters were obtained from their website. Drake's Landing underground storage takes up a volume of 44,500 yards cubed at a depth of 115 feet. The volume of the IM field was calculated by taking the area and multiplying by the same 115-foot depth. It was then determined that the underground storage would take up approximately 4% of the IM field. Next, it was important to look at the solar panels. Drake Landing uses approximately 800 solar panels with dimensions of 2.45 by 1.8 meters. Solely accounting for the panels themselves and no spacing, these panels would take up roughly 13% of the IM field. Last but not least, it's important to look at the amount of energy that can be stored given the volume. If you assume an efficiency of 43%, 600,000 megajoules can be stored. If you also assume that this energy will be depleted over 12 hours, the average power output is 13.8 megawatts. To give this number a little bit of reference, our campus maxes around 3 megawatts. So as you can see, the potential is huge. A few other companies that are exploring thermal energy storage on a larger scale are Ecogen and Malta. In conclusion, Carnot batteries are an emerging technology for thermal energy storage, and their development will be crucial to the expansion of renewable energy storage. During the semester, we accomplished building an ORC engine from an AC compressor to create a proof of concept. While it did not function the way we expected, we believe that may be due to the limitations on the hot water supply. We also completed 7 different in-depth case studies for the application of the ORC engine and other thermal energy storage applications. Given more time, we would use an ideal water supply, as well as look into larger and higher temperature applications of thermal energy storage. Thermal energy storage is an up-and-coming topic that holds the potential for great technological advances. As a group, we would like to thank quite a few people and groups that helped us with our project throughout the semester. First, we would like to thank our advisor, Dr. Richards, a share for the funding of our project, Jim Peisch, Mrs. Henley, and other shop techs for their constant advice and assistance, Robert Goodrich for his help with the electrical wiring on our system, Lonnie Bess and Huzzy's Refrigeration for assisting with the refrigerant, Bon Appetit for supplying ice during our testing, the Grove City College Mechanical Engineering Department, and last but not least, we would like to thank all of you for attending our presentation today. Thank you.
Well, thank you, team. That was very well presented, and I'm going to now open up the floor for discussion from the audience. I would ask you, as you share a question, to if you want to turn on your mic and your microphone for that time, and then mute again when you're done. So if Miranda Griffith would mind turning her camera back on, I'll let her speak to the audience at this time. Thanks. Are there any questions?
Come on, don't be shy.
I'm going to ask one just to help. Go ahead, whoever is chiming in there, please.
So my daughter's going to kill me, but I love her. Look at her. Great job, team. I know you have been working really hard, and
do you have a question? Mrs. Griffith?
I don't have a question, but I am so proud of you.
That's great. Any questions from anyone else? The one I was going to ask. Go ahead, please.
Can you hear me? I have a question.
Yep.
There hasn't been a lot of work done, according to your report, on thermal storage. From what you've learned, would you personally invest in a company that was going to seriously put out thermal storage for homes or small businesses, or don't you know yet?
So to answer that question, and team members jump in if you would like, but I would say at the small scale residential level, I would implement it on my home. My home was actually one of the case studies in this project. However, I have done research into other types of thermal energy storage, such as large scale thermal energy, things of that nature. And when it comes to if I were to actually invest my money, I would say I would be investing in that portion of thermal energy storage, so at a power plant level, those types of things. Does that answer your question?
It sort of answers my question. I guess specifically when I'm looking at your system, you're looking at a couple of expensive items, mechanical items, connections. It's a little on the complex side, and longevity in terms of how long it's going to operate, trouble-free, to do what you want it to do in terms of saving, and you're talking 50% right away. I'm not sure 50% is a realistic money-making target. I don't know. That's why I'm asking if you would invest. I mean, I've known people who've pulled off these kinds of activities, and if they're honest, they are spending more money than actually they're saving. They're learning a great deal, but in terms of our present economy, it's just not cost effective. Most people would find that it's just not workable. So I mean, you're looking at what you produce there. Those are expensive items that you have in your system.
Yes. So we actually did some cost analysis on this. And in terms of the demand increase that we are going to be seeing in the future, as I mentioned at the very beginning of the presentation, electricity and cost of electricity may look quite different in, say, like 2040. In terms of whether or not centralized or decentralized energy is going to be the way of the future, which I don't know that answer. But in terms of that, our goal was to see if something that is already implemented in your home or in your building in the terms of a hot water container is feasible to create the system rather than buying a battery that you don't have in your home already, which would be to some extent a very similar cost, which is why we did like the Tesla and our system comparison. Because if the world is going to turn into renewable energy and we're going to need to store energy, our thought was, why not create a system that would be able to use already available resources as a battery rather than buying and purchasing that battery from the get-go.
I'd like to ask a question if I could. Forgive my question might be unfair, might be grounded in ignorance and way off base, but I wonder if it's at all, if you see any possibility of this sort of a battery being applicable to electric vehicles, even though your research was focused on residences. Do you see this being applicable at all to automobiles?
I'm gonna probably pass that question off. Does somebody from the build team maybe knows more about automobiles want to maybe take that question?
I guess what I would say I'm not sure how feasible it would be to put it actually inside a car, but with the emergence of more electric vehicles, just like in the commercial sector with energy production, that could be a possible use, is being able to store energy to be able to be used for electric cars.
Not to be a naysayer, but on that point, just given the amount of, like, if you're doing it in hot water, you know, our systems were calling for like hundreds of gallons of hot water to store that energy. So that might make it a little bit tough with a car, but the future will tell, I suppose.
Thank you.
I have a quick question.
Yep.
I can see that the temperature differential is the biggest hurdle. With the heat side, how feasible was it to reach, do you think, your target temperature using solar panels? And what are the obstacles, do you think, there? Does that make sense?
Yeah, it does. Meaning, how feasible is it that the amount of energy that a solar panel would produce would actually heat the water enough to be able to store the energy? Is that like the question?
Correct. Can you really gain the high temperature that you need using a solar panel? It's probably more specific.
Right, yeah. I'm going to pass that one to Garrett Rook, who did quite a bit of our modeling and design work. He knows most about the temperatures and things of that nature. So Garrett, can you answer that question?
It would be dependent on the power output of the solar panel itself. We were using a common hot water heater, and while we did not reach temperature needed to on the high side, it's entirely possible augmentations could be made to the system to make it work. So as far as solely a solar panel, I'm not sure, but your house as a whole or residence as a whole would definitely will produce a high enough temperature to complete the process and get you where you need to be.
I have one more thing. I think there's actually a misunderstanding with the solar panel. So the solar panel, it produces energy throughout the day, and your home only uses, there's like peak times where it uses energy. So there'll be excess energy produced by a solar panel, and that's what this system is used for, is to store that energy. So the solar panel is not actually what's heating the water.
Yeah, that makes sense. I just was curious if you could really bank enough to have enough energy to heat to that kind of level. The other question I had was the size of the water tank. I heard some quote that it was 4 times the size of a normal water heater. A normal water heater, typically the average size is 50 gallons. So 400 plus was the thinking. Does that sound right?
Correct. Yes, it was around 475 gallons. And Beth, you can speak to this. Go ahead.
Yeah. So taking the average water heater size as 70 gallons, it's 7 times the volume. Our system would be 7 times the volume. But if you take it just dimensions wise, how it's going to sit in your house, it would be twice width, height, etc. The size.
Great, good thoughts. Thank you.
It is 6:40. This is Geo Richards again, jumping in. We have just a few minutes left before we transition. Are there any remaining questions that we could do in just a minute or two? pause just for a moment here.
Hi, yes, can you hear me?
Yes.
Okay, so my question was how short of the temperature you wanted to get to you fell. You said you had to use the temperature of what you had at the college to heat the water to, but I think you had said there was a target temperature initially you wanted to use, and I just was wondering what the difference was.
Yeah, so I will let, again, Garrett Rook speak to this. However, the other issue we kind of fell short of was the amount of water as well. So for instance, Hoyt only has a 100-gallon tank. So if you're not cycling the water, it's actually very hard to get the correct amount of water in there. But I'll let Garrett Rook speak to the temperature.
So the initial temperature we're planning on using for the high side was 122 degrees Fahrenheit. We had initially a thought of a corporate partner, but that fell through. So we ended up using 113 degrees Fahrenheit, which is 45 centigrade. The temperature wasn't that different, but it was also, as Miranda stated, an issue of the amount of water we had. We could run the system for roughly 15 minutes before the water cooled down from the water heater, or even vice versa. For the second test, we used a tub of ice water to get a cooler temperature. So we were definitely limited by that. The temperature difference wasn't that great, but it's fairly important when producing power in this way.
Well, thank you for all those questions, and I want to thank this team for presenting an interesting talk. We're going to have to move on now to our following presentation, which will start at 6:45. So thank you, team. Great work.
Thanks, Dr. Richards. Good luck, guys.